Humans have looked up at the sky and wondered at the stars ever since the ancestors that ultimately gave rise to the human race were here. The stars, the skies just excite humans intrinsically. Children grow up fascinated by the stars. But all that we see in the stars with our eyes is light. That's electromagnetic waves oscillating electric and magnetic fields that oscillate just at a certain frequency regions of oscillation. And there's ever so much more information about the stars and about the things out in space that comes from other wavelength bands of electromagnetic waves. And so we now have astronomy done with light, with X-rays, with radio waves, with gamma rays, with ultraviolet light, and many different bands of the electromagnetic spectrum. This astronomy has all been created with these other frequency bands in my lifetime. But the laws of physics say that there are actually two kinds of waves that can be created in the distant universe and travel to Earth, bringing us information about what's out there. The electromagnetic waves, which is what we've always used up until now, and gravitational waves. They're the only other kind of wave that we have for exploring the universe. And the gravitational waves, as we understand them, are going to bring us very different kinds of information about the universe that you could never see with electromagnetic waves. For example, gravitational waves created at the very birth of the universe should be travel unscathed through all of the hot matter of the early universe as the universe is very hot and expanding. They don't scatter, they don't get absorbed, they bring the information from the birth of the universe to us today. But electromagnetic waves, they don't come from there. They got absorbed, they scattered, they lost their information. Electromagnetic waves, you can't see the beginning of the universe. When black holes collide, they produce gravitational waves. They produce no electromagnetic waves at all. So if you want to see colliding black holes, you can only see them with gravitational waves. If you want to see the birth of the universe, you can only see it with gravitational waves. It's a whole new way to explore the universe and to explore things that you can't see in any other manner. Confirming the existence of gravitational waves is very important for fundamental physics. Einstein's laws of general relativity demand gravitational waves should exist. If they didn't exist, then something is really badly wrong with our understanding of the fundamental laws of physics. And so confirming existence tells us that general relativity is really on the right track, and the detailed experiments observations that have been done by LIGO primarily up until now show that that's true to very high precision. Confirming existence of gravitational waves for astrophysics, the importance is simply the payoff in terms of observational astronomy over the coming decades and centuries. If you think back to the time of Galileo, that's 400 years ago roughly, he pointed his optical telescope at Jupiter, discovered Jupiter's 4 large moons, and began instrument-based electromagnetic astronomy. And look at where we are now. What a radical revolution in our understanding of the universe has come from those instruments with electromagnetic waves since the time of Galileo. Gravitational waves, now confirmed to exist, are the foundation by themselves and in collaboration with electromagnetic waves through what we call multi-messenger astronomy. They're the foundation for the future of astronomy. And several centuries from now, when our descendants look back on this era, I think they're going to say that one of the great contributions that we gave to them is our understanding of the universe through gravitational waves and electromagnetic waves working together.